Okay, so the last example that we're going to do here, and I just want to do this to sort of clean up any potential misconceptions here. So I'm going to give you a problem that looks like the following. So here's our stress cube, right? And I'm going to give you certain normal stresses, right? And just draw the shear here. Okay, so this is our same, right? I always draw the same diagram. And we're going to say that this is 30 KSI, and this is 50 KSI. Oh, let me just clean that up a little. 50 KSI, right? And the shear is 0 KSI, right? And that's important, right? Because what does it tell us about this state of stress if I tell you that there is no shear, right? Basically what it tells us is this is a principal state of stress, right? Principal state of stress. So here we can draw more circle, right? In this case, I'm going to try to do it a little bit like this here, and sort of go all the way over here with it. So this is tau, and this is sigma, right? And so the first thing we're going to do, right, we know it's a principal state of stress, right? That means there is no shear stress in the xy plane, right? So in this plane, x and y, there is no shear stress. That doesn't mean that there is no shear stress, period, right? I can orient this to a different orientation, and there can be shear stress, right? So let's see how that works out, right? So we know this is a principal state of stress. So let me first plot these guys like we always do, right? So I'm going to come out here 10, 20, 30, 40, 50. So that's plotted right here. So this is 50, 0, right? And then I'm going to go up and plot 30, minus 0, which is basically still 30, 0. Right? And again, you see, just because I have no shear stress, they have to fall on the sigma axis, which means that it is in fact a principal state of stress, right? So I can, let me keep the red here. So this guy here, I'm going to highlight it in red, that is the principal state of stress, right? And I can draw this circle, something like that, right? And the center of the circle here, right, is at 40, 0, like that. Right? Okay. So in a principal state of stress, where my tau xy is 0, right? You could see this guy here becomes tau max, and that actually equals 10 KSI, right? Well, you can either see it, right, which is great. You can sort of see it and identify that is just graphically that has to be the maximum shear stress, or you can calculate it by tau max equals sigma 1 minus sigma 2 divided by 2. Right? And in this case, you can see that's 50 minus 30, which is 20, divided by 2 is 10. Right? Basically, what I'm saying is the diameter right here is sigma 1 minus sigma 2. Right? And my radius is half of that. My radius also happens to be equal to tau max. Right? Okay, so now instead of drawing the orientation of the stress cube, in the principal direction, why don't we try to rotate this thing and draw it as a and draw it as a maximum shear stress, right? So in this case, what I'm going to do, so this is sort of that backwards problem I think we had talked about. So what I want to do is, if I want to orient it for maximum shear stress, really what I want is that blue vertical line. And this guy here is, I'm just going to pull it out, that is just 2 theta, right? I'm not going to call it theta p because we're already at theta p, right? To orient it into principal coordinates would be, theta p would be 0, right? What I want to do is orient this into maximum coordinates, maximum shear stress coordinates. And there you can see that theta equals 45 degrees, right? Because it's 90 degrees on the circle, that means it's 45 degrees on the stress cube, right? So this guy up here, right, is going to end up being 40, comma, and this would be a minus 10, right? And this down here would be a 40 and a positive 10. Okay, so now let's see how we draw that, because this can get a little tricky, right? So let me do this in green, I guess. In fact, let me change all of these guys to green. Like that, okay? So it looks something like this, right? So this is rotated 45 degrees. Right? 45 degrees like that, okay? Now, on all faces, right, so that would be the sigma coordinate, both faces are now 40 KSI, right? So this guy here, this guy here, this guy here, and this guy here. They're all 40 KSI. Okay. Now the big question, and really quite honestly the only question, is how do I plot these, the tau max, right? Which direction is it? Does it go like this, right? Where it's sort of pulling it vertically upward and squeezing it laterally, right? Or does it go more like this, right? Where now it's sort of pulling it laterally outward, right? And sort of squeezing it vertically, right? So how does that work? Well, let's look at our sign convention, and let me, for the time being, just get rid of this guy because I don't want it to mess anything up. Okay, so let's look at how the sign convention works, right? We want to take this point here and we want to rotate it to that point there, right? So that is the X face, that is this face right here, right? And that is getting rotated to this face right here, right? In fact, let me do that in blue. That is getting rotated to that face right there. So on that face, we've got a negative 10 KSI of shear stress, right? So this is my coordinate system now, right? So this is my X prime, and this guy here is my Y prime, because I started and I rotated at 45 degrees, right? So what does a negative shear stress on that face look like? Well, it's a positive X prime face, right? So a negative shear stress would have to go in the negative Y prime direction, like that, right? And then everything else follows, right? all looks like that, right? So that guy there is a negative shear stress. Now that's the actual direction of it, right? I want you to see that because I want you to see that it's really pulling outward, right? Why does that make sense? Because that 50 KSI is a lot more than that 30 KSI, right? So this thing is being pulled laterally, right? Okay. Now for consistency, what I'm going to do is I'm going to draw these in the positive direction, just so we don't get confused. And then I'm going to label them as a minus 10 KSI, just like that. Okay, so they're drawn in the positive direction, and then I'm going to label them as a minus 10 KSI. Just like that. So that means that they're going the opposite direction of the arrows. Right? So I can give you a problem like this where I give you, let's say, a principal state of stress, and then say, tell me what the maximum shear is, right? The correct answer is not 0, right? The only way it would be 0 is if this guy here somehow equaled that guy there, right? If they are the same stress, then if you look what happens, the Mohr circle actually just becomes a point, right? It has no vertical dimension to it, right? It's not really a circle, it's just a point, because my sigma xx and my sigma yy are the same, right? Sometimes they refer to that as a hydrostatic stress, right? So that's sort of a special case where there is no shear stress. And that becomes relevant particularly in fracture mechanics, because as you'll see, steel yields and is ductile in the presence of shear stress. If I somehow expose steel to, a state of stress that has no shear, then I'm in big trouble, because it will not be ductile, it will actually fracture. And that's what we see. That's what we see out in practice. I don't know if you guys followed the news, but there was a recent fracture, I guess about a year and a half ago or so, of the Delaware River Bridge that the Turnpike owns over the Delaware River. And that was obviously a very, very brittle failure. They were very lucky that nobody got hurt, because the entire bridge was probably very close to collapsing. But that was a situation where locally there was a stress concentration, and because of that, there was no shear. There was a huge amount of tension, and then because it was trying to thin out perpendicularly, right, that's Poisson's ratio, and that was being restrained, there was actually tension in fact, in that case, it was all 3 directions. So there was no shear, and that is what ultimately led to the fracture, because it will only yield in the presence of shear stress. If you remove the shear stress, the steel can be very, very brittle, very brittle. Okay, so that is that. I will post these, and then I will post the notes, and I'll see everybody tomorrow.